People tell me quantum theory is abstract, and they said something very similar at the Atomic Energy Commission hearings in 1954. They spoke as though the 100,000 dead in Hiroshima and the 70,000 dead in Nagasaki were abstractions, as though the fireball that rose over the Jornada del Muerto desert on July 16th, 1945 belonged to some other world entirely. I need you to understand something about what I witnessed. I stood in that desert in New Mexico in the darkness before dawn, and I watched an abstraction become a second sun. The light reached us before the sound, and in that terrible, beautiful light I saw what quantum theory actually is. It is not philosophy, and it is not a puzzle for clever men in lecture halls. It is the deepest description we possess of how reality is constructed, and when you grasp it fully, you hold in your hands the power to unmake the world. That is not abstract, and that is the most concrete thing I have ever known. Let me take you back, because none of this began in a desert. It began with a question so simple that most people never bother to ask it, which is what matter is made of. You sit in a chair, and the chair is solid. Your hand rests on a table, and the table pushes back. Everything around you feels permanent and reliable and continuous, and you trust it enough to build your cities on it. But here is the trouble with that trust. At the beginning of the 20th century, we started looking more closely at what things are made of, and what we found did not match what our hands and eyes had been telling us for 100,000 years. The atom, that supposedly indivisible foundation of all matter, turned out to be almost entirely empty space. I used to walk the mesas around Los Alamos, miles and miles of open desert between one settlement and the next, vast emptiness punctuated by tiny concentrations of matter. A cluster of buildings here, a ridge of rock there, and nothing between them but wind and possibility. The atom is like that landscape in ways that most people never consider. If you could see it truly, you would find a nucleus of extraordinary density, surrounded by an immensity of nothing, with electrons existing somewhere in that void, not orbiting like planets, but hovering in a haze of probability. The solidity you feel when you press your hand against a table is not the solidity of substance touching substance, but the repulsion of electromagnetic fields, a negotiation between charged particles that never actually make contact. When the bomb detonated at Trinity, steel towers half a mile from ground zero vaporized in an instant. They did not melt, they vaporized. The electromagnetic forces that had given that steel its apparent permanence were overwhelmed in microseconds, and what that revealed is that the solidity had always been provisional. We did not create fragility at Trinity. We simply exposed it. And that was merely the first surprise, because the deeper we looked, the stranger it became. I went to Europe as a young man, to Cambridge first, and then to Göttingen in Germany, where I studied with Max Born. This was the mid-1920s, and theoretical physics was in a state of magnificent upheaval. The old certainties were collapsing like those steel towers, though we did not yet know what would be built upon the rubble. Niels Bohr, working at his institute in Copenhagen, had already shown that electrons in an atom do not behave like tiny planets orbiting a sun. They exist only in certain discrete energy levels, meaning they can be here or they can be there, but they cannot occupy anything in between. When an electron drops from a higher energy level to a lower one, it emits a precise quantum of light, not a stream or a continuous flow, but a packet, a single indivisible unit of energy. This was Planck's original insight from 1900, that energy is not continuous, but arrives in discrete quantities he called quanta. When Bohr applied this idea to the hydrogen atom, it worked beautifully and predicted the spectral lines with extraordinary precision, but nobody could explain why it worked. The mathematics described the behavior, but the physical picture and the meaning remained elusive, and what we had was a map that was accurate and completely mysterious at the same time. Then came Heisenberg, barely 23 years old, working through the night on the island of Helgoland, and he constructed an entirely new mechanics. He called it matrix mechanics, a formalism that dispensed with the very idea of an electron having a definite position and a definite trajectory at the same time. Around the same period, Schrödinger approached the same problem from a different direction through wave mechanics, and showed that particles could be described as waves smeared across space, existing in a probabilistic haze until the moment of observation. Two roads led to the same destination, though the travelers could not see it at first. Born, my teacher, gave us the interpretation that still stands, which would become the core of the Copenhagen interpretation of quantum mechanics. The wave function does not describe a physical wave. It describes a probability amplitude. You square it, and you get the likelihood of finding the particle at a given location, not where it is, but where it might be. The universe, at its most fundamental level, does not deal in certainties, but deals entirely in probabilities. I remember the atmosphere in Göttingen during those years. There was an electricity to it that felt almost literal rather than metaphorical. We were young men dismantling the classical picture of reality, and we knew it. We felt the ground shifting beneath us, and every week it seemed another assumption fell, determinism fell, locality fell. The independent existence of properties before measurement fell. One by one, the pillars of the old physics cracked and came down, and what rose in their place was something stranger and more beautiful than any of us had imagined. Let me make this concrete for you, because this is where most explanations fail and where most people lose the thread. Heisenberg's uncertainty principle is often described as though it were a limitation of our instruments, as though we simply cannot measure precisely enough, as though the electron has a definite position and we are merely too clumsy to find it. That is a fundamental misunderstanding of what the principle actually says. The uncertainty principle does not say that we are ignorant of a particle's exact position and momentum at the same time. It says the particle does not possess a definite position and momentum simultaneously. These properties are not hidden from us. They simply do not exist in that way. The question of where exactly the electron is and how fast it is going is not a question we cannot answer. It is a question that has no answer, like asking what is north of the North Pole. The question is grammatically correct and physically meaningless. I want you to stop and sit with that for a moment. This is not about the limits of human knowledge. It is about the architecture of reality itself. And here is where things become even stranger than you might expect. When you bring two quantum systems together and they interact, they can become entangled, meaning they are correlated in ways that have no classical explanation at all. Measure one particle, and you instantly constrain the possibilities of the other, regardless of the distance separating them. Einstein called this spooky action at a distance, and he meant it as an indictment of the theory. He believed quantum mechanics had to be incomplete, that hidden variables must be restoring determinism beneath the probabilistic surface. I had great respect for Einstein, and that respect only deepened after the war. We both found ourselves at the Institute for Advanced Study in Princeton, and we walked together often along the quiet streets near the campus, sometimes for an hour or more, discussing these very questions. He never accepted quantum mechanics fully, and I never tried to force the issue. Some disagreements are not about evidence. They are about what kind of universe a person can bear to live in. Einstein wanted a universe of certainty, of objective reality, existing independent of observation, and quantum theory offered him no such comfort. Decades later, a physicist named John Bell devised a theorem that made the entire disagreement experimentally testable, and that changed everything. The experiments were conducted again and again with increasing precision, and they confirmed what Bohr and Born and the rest of us had suspected from the beginning. There are no hidden variables beneath the surface. The correlations are real, and the universe is, at its foundation, non-local in ways that challenge every intuition you possess about how separate things should behave. The discomfort we feel in the face of quantum mechanics is not a flaw in the theory, it is a flaw in our expectations. We evolved to navigate a world of middle-sized objects moving at modest speeds, and our intuitions were shaped by evolutionary pressures that had nothing to do with the subatomic realm. When quantum theory offends our common sense, it is our common sense that must yield to the evidence. But here is the thing that most people never connect, and it is the thing that kept me awake for years after the war. This strangeness, this beautiful and bewildering mathematics of probability, amplitudes, and wave functions in quantum states is not confined to philosophical debate. It reaches up from the subatomic world and seizes the world you live in with both hands. Consider the nucleus of an atom, where protons and neutrons are packed together in a space so small it defies imagination. The protons carry positive electric charge, and positive charges repel one another with tremendous force. By every principle of classical electromagnetism, the nucleus should fly apart the instant it forms, and it should not exist at all. And yet it does. What holds it together is the strong nuclear force, a force that operates only at subatomic distances and whose behavior is entirely quantum mechanical in nature. Without quantum theory, you cannot explain why matter holds together at all, which means the very ground beneath your feet is a quantum mechanical phenomenon. Now consider what happens when you split that nucleus apart, because that is where the story turns from strange to devastating. In 1938, Otto Hahn and Fritz Strassmann were working in a laboratory in Berlin, bombarding uranium with neutrons, and they discovered barium among the reaction products. Barium was an element far too light to be a simple chip off a uranium nucleus, and nobody could explain what had happened. Lise Meitner, one of the finest physicists of her generation, had been forced to flee Germany because she was Jewish, and from exile in Sweden, she and her nephew Otto Frisch realized the truth of what Hahn and Strassmann had produced. The uranium nucleus had not merely chipped, it had split completely in two. That splitting is what we call fission. And in that breaking apart a small amount of mass converted into energy, according to Einstein's relation, E equals mc squared. A single fission event releases energy measurable in millions of electron volts, which sounds small until you understand what comes next. Each fission event also releases additional neutrons, and each of those neutrons can strike another uranium nucleus and trigger another fission event, and the process cascades outward in every direction. That cascade is a chain reaction. I read Bohr and Wheeler's paper on the mechanism of nuclear fission in 1939, and I understood immediately what it implied. Most physicists understood the same thing. The knowledge sat in our stomachs like lead. This was not abstract, and it was not mathematics on a blackboard. This was the mechanism by which a city could be erased in a single flash of light. Think about what that connection means. The same Born probability interpretation, the same quantum formalism that tells you an electron does not have a definite position, is the theory that explains why atomic nuclei hold together, why they can be broken apart, and exactly how much energy is released when they shatter. Every step in that chain, from the structure of the atom to the cascade of fission, is a quantum mechanical process. You cannot get from the periodic table to a nuclear weapon without quantum mechanics. It is the bridge, and it is the only bridge. And we crossed it. In 1942, the Army initiated what became known as the Manhattan Project, and I was asked to direct the scientific effort at its center. General Leslie Groves, the military commander who had built the Pentagon and understood concrete and steel, oversaw the entire operation. I do not think he fully grasped what we were building, not in the way a physicist grasps it, but he understood urgency and he understood scale. Los Alamos became our laboratory, built on a mesa in the mountains of New Mexico, assembled in haste, surrounded by barbed wire, and filled with the most extraordinary collection of scientific minds ever gathered in one place. Fermi was there, along with Beth, who led the theoretical division, and Teller, who was already dreaming of something far worse than what we had been asked to build. Feynman arrived barely out of graduate school and brilliant beyond measure, and von Neumann brought a mathematical mind that operated at a speed which frightened even us. Hundreds of others joined them, theorists and experimentalists, physicists and chemists and engineers, and our single task was to take the formalism of quantum mechanics and nuclear physics and turn it into a functioning weapon. The Trinity device used plutonium-239, not uranium, but an element that does not exist in nature, one we had to create atom by atom in the reactors at Hanford. The implosion design required solving problems of extraordinary complexity, and the critical mass calculations depended entirely on quantum mechanical cross-sections, meaning the probabilities of neutron capture, of fission, of scattering, of absorption. These are not approximations or rough estimates. They are the precise quantities that quantum theory provides. They emerge from the Schrödinger equation, from Born's probability interpretation, from the entire framework of quantum mechanics as we understood it. Without that framework, you could not calculate whether a given assembly of fissile material would sustain a chain reaction or fizzle into nothing at all. We did the calculations, and then we built the device. On that morning in July, in the Jornada del Muerto desert, the journey of the dead man, as the Spanish had named it centuries before, we detonated it. The flash was brighter than anything I had imagined in all the years of preparation. The heat reached us miles away from ground zero, and the cloud rose and kept rising, a pillar of fire and debris climbing toward the stratosphere while the sound came later. A rolling thunder that seemed to rise from inside the earth. I remembered a line from the Bhagavad Gita in that moment. I had studied Sanskrit at Berkeley years earlier and read the great Hindu texts in the original language, and they had shaped something in me that Western philosophy alone could not reach. An understanding that creation and destruction are not opposites, but aspects of a single process, an endless cycle turning through everything. Vishnu is trying to persuade the Prince Arjuna to do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that one way or another, standing in that desert. Let me say this as plainly as I know how. The wave function of a uranium-235 nucleus, that mathematical object, that probability amplitude existing in Hilbert space, is the reason Hiroshima was destroyed on August 6, 1945. The quantum mechanical tunneling probability that allows a neutron to penetrate the nuclear potential barrier is the reason 100,000 human beings died in a fraction of a second, and 70,000 more died in Nagasaki 3 days later. The uncertainty principle, the superposition of states, the probabilistic nature of nuclear interactions, none of these are curiosities for a lecture hall. They are the machinery of the most destructive force human beings have ever wielded. And the reach of that machinery extends further still in every direction you look. The very sunlight that sustains life on this planet is produced by quantum mechanical processes in the core of the sun. Hydrogen nuclei fuse into helium through quantum tunneling, a process that classical physics says is forbidden entirely. The probability of two protons overcoming their mutual electromagnetic repulsion and fusing is vanishingly small for any individual pair. But there are so many protons in the sun, and the process occurs over such immense time scales that it powers a star for billions of years. Without quantum tunneling, the sun would be cold and dark, there would be no warmth and no photosynthesis and no life, and there would be no one left to call quantum theory abstract. The same tunneling that lights the sun is the tunneling that makes a chain reaction possible. And that means creation and destruction are bound together in the same mathematics, the same fundamental process. The Gita understood this long before we wrote our equations. After the war ended, as the Cold War calcified, and the arms race accelerated beyond what any of us had anticipated, I argued against the development of the hydrogen bomb. The thermonuclear weapon is what Teller and others at Los Alamos had called the super. And my opposition was not because I believed the physics was wrong. The physics was as clear and beautiful and merciless as ever. I opposed it because the power we had already unleashed demanded a moral reckoning that we had not yet begun to undertake. As chair of the General Advisory Committee of the Atomic Energy Commission, I recommended against the super's development and advocated for international control of atomic energy, which was outlined in the Acheson-Lilienthal report as a proposal that would have placed nuclear materials under international authority and made the arms race unnecessary. That proposal was rejected. The Soviets tested their own bomb, and the race continued. Some called me naive for my position, and others called me a security risk. In 1954, the Atomic Energy Commission convened a hearing that stripped me of my security clearance, a proceeding that felt less like a trial than a ritual of political destruction conducted in the paranoid atmosphere of McCarthyism. But I do not regret what I said during those years. The knowledge we had gained could not be placed back inside the equations, because it had entered the world and it would proliferate. It would flow into weapons, of course, but also into technologies I could not have predicted in their specifics, even though I foresaw their inevitability. That is the nature of understanding. It does not stop, and it finds every crack. It flows into every application that physics will permit, from medical imaging to energy technologies to the computational devices and communications networks that now encircle the planet. All of them draw, in one way or another, on the quantum mechanical understanding of matter that we assembled in those fevered years. The lesson I carried from Los Alamos, the lesson that has never left me through those walks with Einstein and Princeton, and through the humiliation of the hearings and through every quiet evening since, is this: knowledge is not neutral. The quantum theory that Planck and Bohr and Heisenberg and Schrödinger built, that Born and Dirac and so many others refined into the most precise and powerful description of nature ever achieved, does not exist in a vacuum. It exists in a world of human beings, with ambitions and fears and loyalties and hatreds, and what they do with knowledge depends not on the knowledge itself, but on who they are and what pressures they face. The physicists have known sin, and this is a knowledge which they cannot lose. When someone tells you that quantum theory is abstract, that it has no bearing on your life, that it is merely a mathematical game played by specialists in rooms you will never enter, I want you to remember that morning in the desert. I want you to remember the light that was brighter than 1,000 suns. I want you to understand that the most abstract ideas human beings have ever conceived turned out to be the most consequential ideas human beings have ever deployed, and the distance between an equation on a blackboard and a city turned to ash was bridged not by malice alone, but by understanding, by the patient and beautiful and terrifying work of minds trying to know how the universe is built. That is the burden of knowledge. Not that it might be wrong, but that it might be right, and that what is right about the universe does not wait for us to be ready. Quantum theory is not abstract. It is the structure of every atom in your body, and the fire at the heart of every star, and the force inside every weapon that could end this civilization in an afternoon, and the principle behind every technology that connects you to the rest of the human race. The question was never whether the theory was real. The only question that ever mattered was what we would do once we understood it. We have not yet answered that question well enough, and that is not a problem of physics. That is a problem of the human soul.